questions in the worksheet of St. John's. The force between 2 point charges separated by certain distance in air is F. If each of the two charges is going to be halved, imagine, let me try to write in here, screen right. Okay, so I'm going to write the charge Q and Q, and the force between the two charges is F, and I'm going to halve the two charges Q by 2 and Q by 2, and the distance between them is not R anymore, that's also being halved, R by 2. Then the new force will be actually F is equal to, in the first case, K Q square by R square, in the second case F Q square K Q square by 4 by R square by 4. The 4 and 4 get cancelled, remains unchanged, so it's still F, and that's the answer. I hope you're clear. So let's go to the next question. The electric flux emanating from a sphere of radius 2 meter is phi naught or phi. The radius of the sphere is going to be 4 times more. That would never affect the flux, because flux is the number of field lines. As the radius is increasing, also number of field lines will never change. The flux will remain unchanged. So D is the answer. Let's go to the next question. An electric dipole consists of two charges, plus 2 microcoulomb and minus 2 microcoulomb, which means it's like a dipole, yeah, separated by distance of 2a, which is 4 centimeter, kept at an angle of 30 degree with the electric field. Electric field's value is given. The torque experienced. What is the formula for torque? Torque is equal to PE sine theta. P is nothing but either of the charge into separation is 4 centimeter, 4 into 10 to the power minus 2, into electric field is 1 into 10 to the power 5. The sine theta is just sine 30, and the charge is 2 microcoulombs, so 2 into 10 to the power minus 6. On solving this, you get the answer of torque. Torque is force into perpendicular distance, so Newton meter should be the SI unit. So you can just simply calculate this, and that's about this question. So let me run through the next question for you. How many field lines will emerge from 1 coulomb of positive charge? So how many electric field lines will emerge from 1 coulomb of positive charge? Okay, you know that the electric field lines that's present in vacuum, number of electric field lines is epsilon naught, which is what is 8.854 is the screen brightness, which is what is 8 point screen right. So we know epsilon naught value is 8.854 into 10 to the power minus 12. How many, that's the number of field lines in vacuum. How many field lines will emerge from 1 coulomb of positive charge? So field lines means we can talk it as flux, and flux is equal to Q by epsilon naught. Its Q is 1 coulomb. Okay, and the charge is epsilon naught is 8.854 into 10 to the power minus 12. So which of this is suiting the answer? C is the right answer. That's the number of field lines is going to emerge out. So let's go to the next question. An electric dipole of dipole moment P has been given 2 into 10 to the power minus 6 centimeter. No, that's called that's coulomb meter. Is placed inside a closed surface. The electric flux through the surface will be 0. Obviously, because if you have a dipole which has got minus Q and a plus Q, the net charge enclosed will become 0, and so then the electric flux through the surface is 0. So next is, in a non-uniform electric field, a dipole will have translatory as well as rotational motion. True. I told you this when the electric field is going to be like this, which is non-uniform, where here the electric field is greater. Consider this point is A and this point is B. EA is greater than EB. The force towards the right side will be more than the force towards the left side, which constitute to the torque. So it will drag the dipole towards the right side. Apart from experiencing a rotational motion, it will also experience a translatory motion. So let's go, the assertion is true. In a non-uniform field, the dipole experiences a force as well as torque. Yeah, that's right. So that's the right explanations too. So that's done. In a region of uniform electric field, phi into 10 to the power 3 I Newton per coulomb, which means the electric field is along the x-axis. Find the flux through the square of side 10 centimeter, which is placed parallel to the y-z plane. We have dealt with this question, it was there in Aurora. Supposing this is x, y and z, A plane is parallel to YZ plane. Okay, its normal, that is area vector, will be along x-axis. And you know the electric field is also along the x-axis. The angle between the electric field and the normal vector, that is the ds vector, is 0. Now if the plane makes an angle 30 degree with x-axis, find the flux through the surface. Okay, so in a region of uniform electric field, find the flux through the side of a square of length 10 centimeter whose plane is parallel to YZ plane. So then flux is E ds cos 0. You know the electric field's value, you know the area vector. Area is 10 into 10 to the power minus 2 the whole square. Ds cos 0. Fine. Cos 0 is 1. The first one has been answered. Now if the plane makes an angle 30 degree with x-axis, the plane's normal will make an angle 60 degree with x-axis. This is something you need to really understand. If the plane makes an angle 30 degree with x-axis, the plane's normal will make an angle 60 degree with the x-axis. And so find the flux through the square. So in that case, flux is E ds, you know electric field's value, you know ds value. Cos 30, no, cos 60, that's something you should not forget. It's not cos 30, it is cos 60. So let's go to the next question. In the figure, there are 3 infinite long thin sheets having surface density plus 2 sigma, minus 2 sigma, plus sigma. Various surface charge densities has been given. Find the magnitude and the direction of the electric field at A, B, C and D. So let's look at the point A. Due to 2 sigma, there will be an electric field which is emanating from here, which is 2 sigma. It's minus 2 sigma by epsilon. Let's call it as EA. Due to the negative 2 sigma, there will be an electric field will be terminating. That will, let's call it as I don't know. This is, let's call it as plus due to 2 sigma. This one is due to minus 2 sigma, and due to that this sigma here, it will still emanate from positive. It will be E due to sigma. So these two are in one direction, which is negative direction, and the 2 sigma is terminating here, and so this is in the opposite direction. So let's sum it up to find the electric field at A. To find the electric field at A, you know that it's 2 sigma by epsilon naught. You know that at any point it's it's sigma by 2 epsilon naught. Sigma by, so but sigma here is 2 sigma, right, by 2 epsilon naught. The general formula is sigma by 2 epsilon naught, and it's independent of R, you know, but it's for EA it is 2 sigma, so 2 and 2 get cancelled. For the next one it's minus, and that too this is to be negative sign, and EB will be terminating positive, so plus. We have already drawn the direction, so never take the negatives and positives. Left word is negative, right word is positive, that's all. So 2 sigma by 2 epsilon naught, again this and this get cancelled, and due to the sigma it's facing away from it and it's negative direction, so minus sigma by epsilon naught. This and this get cancelled. You still have minus sigma by epsilon naught to be the net electric field at the point A. Like that we can find for B, C and D. So this is what I said. You can see from this picture here. Okay, I'll just click on the picture. This is the answer. From plus 2 sigma, from minus 2 sigma, from the plus sigma, how you have to draw how is it emanating from positive, terminating in negative at A, B and C, and determine the electric field, and I have given it for A, B and A, B, C and D. This is the method that I have taught you, is something that you need to follow, and this is the answer. I hope you're clear. Okay. So define an ideal electric dipole. An ideal electric dipole is one where two opposite charges are separated by infinitesimally small distance. Generally, the distance has to be 2a. That's something you already learnt. But I am saying don't say 2a. It is some infinitesimally small distance. And then that's called an ideal dipole. An example of an ideal dipole, this thing is a H2O molecule where it is got where the positive and negative charge are very close together. So an ideal dipole is also referred to as a point dipole because the distance between the two opposite charges are very negligible, infinitesimally small. Okay, I hope you're clear. Almost it's like the distance between the two charges, 2L, is approaching 0. Okay, that's what it implies. And an HCl molecule, H2O molecule can be an example. Let's go to next question. Derive an expression for torque experienced by the electric dipole in uniform electric field. What is the net force acting on this dipole? And that is something, torque is equal to P sin theta. That derivation you can write. And in a uniform electric field, the net force acting on the dipole will be 0. And that's why it's only undergoing a torque. But if it's a non-uniform electric field, there will be a net force towards the direction of the stronger electric field. I just drew it before and I explained also. So let's go to next question. The surface charge density of a large conducting sheet. The surface charge density is 17.7. Sigma has been given. It's charged by area. The electric field intensity at a point just outside the sheet. Oh, is it an infinitely plane sheet? Can we take it as an infinitely plane sheet, large conducting sheet? So the formula is sigma by 2 epsilon naught. Sigma is nothing but the surface charge density. So can I write 17.7 in 10 to the power minus 6 by 2 into epsilon naught, which is 8.854. And so you can calculate and write the answer. So let's go to the next question. See, they haven't mentioned it that this is a infinitely large plane sheet. That word is not there. They've just said the surface charge density of a large conducting sheet. A large conducting sheet is different from infinitely non-conducting sheet. It differs. Okay. The theory that I taught you for an infinitely plane sheet was actually an infinitely non-conducting sheet, basically, because the charges resided a positive charge on the right side and left side. We had a horizontal cylinder. We got the electric field to be sigma by 2 epsilon naught, if you remember. But we cannot use that here because they very clearly specified this to be a large conducting sheet. Point number 1, a large conducting sheet, the charge resides on the surface. Yeah, and according to Gaussians, just outside the surface, the electric field is sigma by epsilon naught. For a large conducting sheet, the electric field just outside the surface is sigma by epsilon naught. It's not sigma by 2 epsilon naught because that was for an infinite non-conducting sheet. Because in a conductor, the electric field inside is 0. Okay, the electric field, if it's going to be a conductor, the electric field inside the conductor is going to be 0 and all the flux emerges from the outer surface. So then therefore when you calculate the value, the option that you can choose is 2 into 10 to the power 6. That is 17 sigma by epsilon naught, not 2 epsilon naught. However, if you see here, the option doesn't even match. So should we be taking it as an infinitely large non-conducting sheet? That's the question that you have to go back and ask your teachers, because the answer has to be 2 into 10 to the power 6. And here it is, none of these answers is matching. They seem to be putting sigma by 2 epsilon naught as a choice. So see, basically this is the difference. Okay, let's take this diagram. This is a charge conducting surface. When they say charge conducting surface and they ask for the electric field closer to it, then it is only sigma by epsilon naught, because we consider only that surface from which the charge is emanating, unlike the previous derivation in which I got sigma by 2 epsilon naught, where I considered that was a non-conducting, infinitely large non-conducting surface. plain sheet, in fact, where there will be charges on the other side also, and there will be a horizontal cylinder, and there will be electric field emanating from both sides. So it became sigma by 2 epsilon naught, but in this one it's sigma by epsilon naught only. So this is something that St. John's need to clarify why the options are incorrect. So now let me read 11th question. Figure shows the electric field line in which an electric dipole is placed as shown in the figure. Which of the statement is correct? You can see that the electric field on the left side is stronger than the electric field on the right side. So it will eventually move towards the left because the force on the left side on the negative charge is greater than the force on the positive charge, and so then it's going to move towards the left. It will also experience torque, of course. There is a net force, so the dipole will not experience any force. No, the dipole will experience a force towards right. No, the dipole will experience a force towards the left is correct. Apart from that, it will also undergo a torque. Will it? Let's see. The angle between the dipole and the electric field in this case is 0. The torque will be 0. So in this case, since it's not making an angle with the electric field, we can just say that there is a net force and therefore the dipole moves towards the left. So that answers that question. Let's go to next question. I think this is the 12th question where the question is not clear. The options are straight away given. A flux through the surface of the sphere. Okay, I need to read this question. I need to understand what this question is. 1 second, hold on. So they've given this diagram, and you can see that there is a capital Q at the center and a minus 2Q at a distance r by 2 from the center. So the net charge through the sphere is Q minus 2Q is minus Q. So the flux is net charge minus Q by epsilon naught is the flux through the spherical surface. Option A is right answer, true. Next question, B. The field on the surface of the sphere is minus Q by 4 pi epsilon naught. You know the net charge is minus Q at the center. 1 second, hold on guys. Sorry. Okay, let me continue. The field on the surface of the sphere is minus Q by 4 pi epsilon naught into r square. Provided we can say that provided there is a, why can't option B, the question B be right? They're saying it's false because there's a Q and minus 2Q and they're not located exactly at the center, and the positions are there at different points. So therefore the field on the surface of the sphere is not minus Q by 4 pi epsilon naught into r square. 1 by 4 pi epsilon naught into Q by r square. The r distance is different for Q and minus 2Q, and so we cannot consolidate and write the electric field like that. We can write for the total flux based on the charge enclosed, but not the electric field based on the charge enclosed. Electric field depends on the position of the charge. So the second B is false. The flux through the surface of the sphere due to phi q is 0. Yeah, because phi q is located outside, so that is also true. That's 0. So A is true, C is true, B is false. And D, field on the surface of the sphere due to minus 2q is the same everywhere. On the sphere, minus 2q is not even having a symmetry. It's located somewhere towards the lower side of the sphere. So there is no spherical symmetry. Therefore, that is also false. So let's go to next question. The two charges minus q and minus 3q are fixed on the x-axis, separated by distance t. Where should a third charge 2q be placed such that it will not experience any net force? Okay, let me try to write it. Screen right. Okay, so then there is a charge minus q and a minus 3q placed on the x-axis separated by distance d. Where do you think the 2q can be placed so that does not, so you just place the 2q in between so that the net force experienced by it has to be 0. You know that the 2q will be attracted by this negative charge, and the 2q will get attracted by this negative charge. You can just equate both these forces, this force and this force, which is k into, don't write negatives and positives, k into q into 2q by this is x, and this can be d minus x by x square is equal to k into 2q into 3q by d minus x the whole square. Okay, the k and k get cancelled. The q square also is getting cancelled. You have a 2 into 2 and 2 also gets cancelled here. So you're still left with a 3. So it's a 3x square is equal to d minus x the whole square. So can I write root 3x is equal to d minus x and consolidate x into root 3 plus 1 is equal to d. So x is equal to d by root 3 plus 1. So let me go to next question. A spherical conductor of radius 12 cm has a charge of 1.6 × 10⁻⁷ coulomb distributed uniformly on its surface. What is the electric field at a point P from the below mentioned 3 cases? Spherical conductor of radius 12 cm. So in the first case is r by 2, which is interior to the conductor, right? It's enclosing a charge 1.6 × 10⁻⁷ coulomb distributed uniformly on its spherical surface. Oh, then which means are they on its surface, not interior. It is not, does not say anywhere it's a homogeneous solid sphere. Okay, so I can take it as a metal cavity and say that for the first case the electric field will be 0 at a distance 12 cm is on the surface. So on the surface is k q by r square, where the small r is capital R, both of them are 12. So constant, and at a distance 2r means that it's going to be outside of the conducting shell, and you know there it's directly proportional to small r, the position vector, and inversely proportional to capital R cube, or it's not proportional. The formula will have a small r by capital R cube, if you remember, for outside of the spherical shell. Just have to substitute those formulas in there and then get your answers. So for 2r it's going to be outside of the sphere. Outside is not directly proportional to smaller. Outside will be just k into q by the whole distance 2r the whole square. That's all. Instead of r square it's 2r the whole square. So just substitute those formulas and get your answer. Okay, so next question is: a positive charge is placed near an isolated conducting sphere. The electric field is best given by. Positive charge is placed near. Okay, which of these diagram is correct? So started to record. You know that from a positive charge it has to emanate from positive and should also go normal to the surface. So identify a diagram where it's emanating from positive, it's also going normal to surface is 2, because the first one is emanating from positive but it's not going normal to the surface. The first one, it should go normal to the surface. That's very, very important. Definitely these are not going normal. I think the one where is exactly goes normal to the surface, it's appearing as if the second one is wrong. The first one is correct. So it emanates from positive, goes normal to the surface, and again also emanates from because if the near end will acquire negative, the far end will acquire positive. So the option 1 is the right answer. So let's go to next. That's all. The paper is over. Let me try to screen write the answer for this question. Okay, the 3 charges are placed at the corners A, B, C of an equilateral triangle of side 0.5 meter, and the charge at A is a plus 4 microcoulomb. The charge at B is minus 2 microcoulomb. The charge at C is +1 microcoulomb. Calculate the net force on the charge A due to the other two charges. Means you know that the charge at A will be attracted by this negative charge. The charge at A will be repelled by this positive charge at C. So then you have this is about the force, right? The question is about the net force. So there's a force due to C and this is a force due to B, and you will have a resultant like this. And you know this angle is definitely that's an exterior angle which is a 120 degree, and so you can find the resultant F by using root of FB square plus FC square and this parallelogram law plus 2 FB FC cos 120, and cos 120 itself is minus 1 by 2. You all know cos 120 itself is negative, and it's going to be minus 1 by 2, and so this will become negative, and the 2 and the 2 get cancelled. You just have to calculate now what is FB and FC and plug in these values here. They are not equal forces, right? Because this is from C it's from 1 microcoulomb between 1 and 4. For B it is from 2 and 4. So but the distance are the same. Since C, the force due to C is from 1 to 4, the force due to B is from 2 to 4. Can I say force at B is twice the force at C? So can I write, can I call this as F? And can I call this as 2F? So it's 4F square plus F square minus, FBFC is, what is FB? It's 2F. And this is F. So it's minus 2F square. So you already have a root of 5F square minus 2F square, which will result in root 3F square, which will result in root 3F. And what is F is between these two charges. So root 3 into K into the charge 1 into 10 to the power minus 6 into 4 into 10 to the power minus 6 by the distance which has been given to be 0.5. The distance was mentioned as 0.5 meters. So 0.5 the whole square. You just substitute the value of K and you can get the answer. So that's how you do this sum. I hope you're clear. So next question is, according to Coulomb's law, between law of force between two charges, F is equal to K Q1 Q2 by R square, what will happen if one of the charges is 0? One of the charge is 0. You can consider that another charge would be at infinity. Can I say that? So basically, no, you know, of course, when there is a charge on the surface of if there's a charge present in front of us, if it's positive, you can imagine that there will be a negative charge at infinity. But infinity means R square becomes infinity square, and so then force anyway becomes 0. Therefore, yeah, our assumptions is right. We can consider that if there's only one charge, there's definitely another charge. There may be force of attraction repulsion, but the distance happens to be at infinity, and so then therefore the force itself becomes 0. They say this is the reason. Another reason this is one of the charge itself is 0. No, but I wouldn't agree with it, because for me, yeah, the force is between two charges, and if you see one charge here, there has to be another charge somewhere, because electric field is always emanating and terminating somewhere, so there has to be a charge at least at infinity. So then we can say that there is no attraction or repulsion. The force is becoming 0. Okay, can we keep it like this? So let's go to the next question. What will be the permeability of the medium? Permittivity of the medium, which has dielectric constant 5.4. The medium's permittivity is a dielectric constant K times absolute permittivity, which is 5.4 into 8.854 into 10 to the power minus 12. Just multiply and find out which option is correct. Okay, so let's go to next question. Dimension for epsilon naught. The dimension of epsilon naught You know the SI unit for epsilon naught is the reciprocal of K, whereas K is Newton meter square per coulomb square. So it's per Newton per meter square coulomb square. So let me write it now. Per Newton per meter square coulomb square is the SI unit of epsilon naught. And you want the dimensional formula. What does Newton stands for? Newton is mL t to the power minus 2, the whole to the power minus 1. Meter square is L. Meter to the power minus 2 is L to the power minus 2. And coulomb is ampere. I is equal to Q by T, so ampere into time. So it's ampere square and time square. Just solve this and get your answer, and whichever is the right answer you can mark it. So it's just have to solve it. It has to have m to the power minus 1. Everything has got m to the power minus 1. It has to have L to the power minus 3. And everything seems to have that also. T to the power plus 2 and T to the power plus 2, T to the power 4. So it has to have T to the power 4. And they've represented as whole square, so I think option number C would work out. You can always check out. And there is also ampere. There has to be an ampere. And what are they mentioned? They are mentioning I instead of ampere. That's okay. And ampere square, so as I square. Okay, so let's go to next question. The Coulomb's law is valid for any distance between the particle. Coulomb's law is valid for any distance between the particle. So let me tell you this. Coulomb's law is valid for any distance between the particle. See, I just told you infinite distance means the force is becoming 0. I don't know what to say, false or true, because Coulomb's law is generally valid for any distance between two particles, two charged particles, then it's true. But actually speaking, when the charged particle gets too closer, too closer, then the force starts to dominate, and it's becoming like a nuclear force, such a short range force. So I'm not sure what your teachers wants for this. Okay, you can go and ask them. See, when the infinity is the distance, the force becomes 0. So can I say Coulomb's law is valid? I can say that and say that the force becomes 0, so I can say that. But when the distance between the two charges is infinitesimally small, which makes the force much larger, and it is so small to the extent that it is about 10 to the power lesser than 10 to the power minus 15, which will be like the distance between the two nucleons in the nucleus. Then the force is no more called electrostatic force, it's called nuclear force. So what do we say? So I would say that it's false, because very smaller distances like 10 to the power minus 15, lesser than that, becomes a nuclear force. I can say false. I don't know. So you have to check on this with your teacher who set up this question paper. It's a perception. So let's go to next question. An electric dipole, when held at 30 degrees with respect to uniform electric field, experience a torque of 9 10 to the power minus 26 Newton meter. Calculate the dipole moment P. You know, torque is equal to PE sine 30. Just substitute all the value. You know, when sine 30 means it's half the maximum value, and the maximum value is PE. They've given, they're asking you to find the dipole moment. Okay, you know that. Okay, you can write torque is equal to PE sine 30. So P dipole moment is torque by E sine 30. Okay, you've been given the electric field, you know sine 30, you know the torque, you can find the dipole moment P. Write the answer in coulomb meter. So an electric dipole is placed at an angle of 60 degrees with the electric field of magnitude 4 × 10 to the power 5 Newton per coulomb. It experiences a torque of 8√3. If the length of the dipole is 4 cm, determine the magnitude of either of the charges. So no problem. You know that torque has been given. It's PE sine 60 P itself you should write as Q into 2A, and the 2A itself is 4 centimeter, with which you can find the value of Q. Q, rest of the values is known. So that's about that question. Let's go to 23rd question. 2 point charges, each of 5 microcoulomb, but opposite in sign, are placed 4 centimeter apart, which means it's a dipole. Calculate the electric field intensity at a point distance 4 centimeter. Okay, since the 2A is 4 centimeter, from the center it's 2 centimeter. So you're trying to find the electric field at a point 4 centimeter from the midpoint. You can say that R itself is 4 on the axial line. E axial, what is the formula? It's KPR by R square minus A square the whole square. Just substitute what is R. R is 4. What is A? A is 2. What is P? P is either of the charge 5 into 10 to the power minus 6 into electric field. 2P Q into 2A. Have they given the distance between the two charges? 4 centimeter. 4 into 10 to the power minus 2. So substitute everything and get the answer. It's axial lines formula. So that's about it.